Good morning, everybody. Thank you for joining our session here. This is milking the most out of thousands of Kubernetes clusters with Chick-fil-A, and I know we've got good competition next door with Lyft talking about service meshes, free chicken sandwiches for all of you if you stay throughout the end. I wish that was true. We didn't know how many people to cook for. So, but we're super glad you're here and looking forward to sharing with you about what we're doing at Chick-fil-A. So my name is Brian Chambers. And I'm responsible for our Internet of Things capability at Chick-fil-A, as well as what we do around computing at the edge, which is in our restaurants. Super happy to also have Caleb Hurd with me as well. And Caleb is an SRE that's focused on those two platforms and who helps us operate those things effectively at scale. So let's get started with giving you a sense of what to expect from the session. So first, I want to make sure you understand really what do we do at Chick-fil-A, what are some of the challenges we have, and why are we doing anything with significant technology? Why is Chick-fil-A here at this conference talking about Kubernetes? So we'll explain kind of our problem space, help you understand that a little bit better, and then answer the question about how we're actually using Kubernetes at the edge in our restaurants. I'm an architect by background, so I have to tell you about our architecture. So we're going to share about that and how that works. Then the majority of the time is really going to be talking about the fact that Kubernetes is really awesome, but there's certain things that are true for us at our kind of scale that are probably true for you in the nature of the business that you work in, where Kubernetes is an awesome platform, but you have to do some engineering around it to actually be able to fully take advantage of it. And so we're going to share a couple areas where that was true for us, and then the solutions that we came up with and how we've solved those problems. And then our hope is to have some Q&A time, significant Q&A time, so we'd love to answer your questions. And then we'll, of course, hang out at the back at the end so the next session can come in. But if you want to find us and chat one-on-one, we'd love to talk with you more. So with that said, how many of you guys have been to and eaten at a Chick-fil-A restaurant before? Show of hands. Awesome, I love it. OK, so if you haven't, that triangle kind of to the top right of the map here, you are right in the middle of it right now, sitting here in Times Square. So there are 3 Chick-fil-A's within a couple minutes of you. And if you want to get up right now and leave the session and go eat there, no judgment at all. Go for it. You're good to go. But if you have been to Chick-fil-A, you've probably seen something that looks a lot like this. This is a picture from one of the New York locations. You've got people just packed in lines outside. If you're from a suburban area, you may have been in a situation where you've sat in a drive-through line that's wrapped around the building, maybe even twice. And our restaurants are super, super, super busy. And that's a good problem, but it creates some interesting challenges. So just to throw some stats out there to help you get a handle on this, this is a little dated, but pretty accurate for an average restaurant in terms of how much product is actually going across the counter of our restaurants at any given time. So there's a lot of stuff happening. And like I said, this creates some capacity challenges. So average Chick-fil-A restaurant, 6 days a week, we're closed on Sunday, does more volume than any of our competitors do in that full 7 days. And we have a lot of restaurants that were built with a certain sales volume in mind. Can't tell you the exact number, but they're doing more than triple that amount. So again, pressures on the ability to actually work in that restaurant to be able to make great experiences for our customers. What we want is for you to come through and get hot, fresh food, a great connection with somebody personally, if that's what you're looking for. If you're racing through the drive-through because you're off, we want it to be fast and convenient for you. But all of this volume has gotten to a point where it makes it very challenging to continually execute on that in the way that we want to. So we at Chick-fil-A, Caleb and myself included, we believe that a lot of the solutions to these capacity problems that we have and the other challenges in our business are rooted, the solutions are rooted in technology. And so where this led us is we started down the road, and I shared about this at QCon last year, about having an Internet of Things platform in our restaurant. And the thinking there is really this. If you're able to take your kitchen equipment and make it smarter, if you're able to have screens that drive our food production, and help people make just the right amount of food at just the right time, streamline, streamline that process, that can really help us achieve those goals. Really fast, great service, great customer experience. And as we started to connect things in our restaurants and think about what that meant, and we wanted to have the capability to actually run critical business functions, even automating product production somewhere down the line, we realized that having a dependency on an internet connection that could be of varying quality, could be really great, or it could be really slow and really terrible, was going to be a challenge. And we knew that there were going to be things that we were trying to react at the speed of customers coming in and out of the restaurant. And so latency, really low latency, is very important to us as well. So that led us down the journey of establishing an edge computing footprint for our restaurants. And what I really mean by that is computing at the edge is just taking compute like you would have in the cloud, but putting it close to the action. For us, this is in the restaurant. For you, this could be at your different business sites. Anybody in retail probably has a similar paradigm, but it's pushing that close to where the actual action is taking place, and then running a lot of the core business from there, and then tipping back to things where you can depend on the internet and the cloud as it makes sense. So that's what we're doing. I want to share what our architecture looked like at this time last year. So just to give you a real high level, you'll see there's a kind of a control plane in the cloud. For us, that runs in AWS. We were running Docker Swarm at the edge last year, and that's changed. We'll obviously talk about that a good bit today. And we have a series of core services. We really think of our edge computing platforms in restaurants as kind of like a tiny little micro private cloud environment. We want developers who want to build things to impact the restaurant to really have the same paradigm they have deploying something to AWS. There's some helpful core services there, like authentication and authorization, messaging, et cetera. And then they have the ability to deploy containerized apps at the edge. And then, of course, there's connectivity and things. We're not going to spend a lot of time on this. So here's how things have changed and kind of where we are today. And so the little dashes around the things are the pieces that changed from the last slide. So the first thing you'll note, and obviously you're a smart group, but it was also in the title, we've moved away from Docker Swarm, and we're running Kubernetes in our clusters at the edge instead. And we're going to tell you a little bit about why we made that decision in just a moment. With that change, we've introduced core DNS at the edge. So we actually run DNS for both our Kubernetes cluster as well as for the rest of the restaurant LAN. So anything that needs to discover services and look things up, we provide that as a service in the restaurant. We've actually just started to use the Istio traffic ingress gateway. I believe gateway is the new name. And while it's still tagged in alpha, we had some good conversations with people that gave us a high degree of confidence that it was a good enough point that we could feel confident using that. And we're really excited about Istio. We'll talk a little bit more about that in a few minutes. And then since we're in a Kubernetes ecosystem, we had the opportunity to use Prometheus from a monitoring and metrics collection perspective. And the way that we do this is just like it looks here. Prometheus actually runs at the edge in each of the restaurants and does local collection and then pushes things back up to the cloud so we can get consolidated views and check on statuses of canary deployments and all those kinds of things that you would do more at the above restaurant control plane level. And then on the top right, you'll see Fleet. We're going to wrap the talk up sharing what Fleet is. It's how we do restaurant deployments, but I'm going to defer that one until a little bit later. So why the switch from Swarm to Kubernetes? Well, the first thing I want to answer is why run containers in a fast food restaurant in the first place? And really, at the end of the day, this comes down to a core thing that we believe, which is what you see on this slide. We believe that an idea in and of itself doesn't really have any value. And we actually believe, even though we're engineers, we believe the same thing about code. We believe that code itself doesn't really have any value. The place where we get value and where we get impact on our businesses is when we're able to take ideas, turn them into code, and take code and get it into production. And that's where we begin to learn real things from real users, get real feedback, and actually be able to begin to build something that can impact our business. So at Chick-fil-A, we want to optimize for going through that process iteratively as quickly and rapidly as possible. And what we feel is that there's a lot of things. If you think about an application, a lot of what actually you have to do with an application, it's not building your core logic. It's all the little things around it. It's all the security-related things. It's all the traceability, the monitoring, the introspection. Those are the things that end up taking a lot of time. Sometimes writing services that do things well, simple microservices, is actually really, really straightforward and easy, and you spend all your time in the area around it. We're excited because we think the Kubernetes ecosystem is one that is bringing a lot of tools to bear that are going to make that process a lot easier for developers. And what they're talking about with service meshes next door, what Istio is bringing, there's opportunities to offload a lot of that heavy lifting into sidecars in pods in Kubernetes. And so we wanted to make a switch into a place where we were going to be able to take advantage of those developments in the industry. Swarm was cool. We really feel like the future is Kubernetes, and we wanted to be kind of on that train, getting the latest and greatest development that was coming out there. Now, we did not switch to Kubernetes because it was the cool new thing. So last slide I have here on this topic, book I'd recommend you check out, but Accelerate is a research-based approach to what makes engineering teams successful. Getting some thumbs up out there, awesome. Really great book. using the greatest technology, the newest stuff, has no correlation at all to the success of your project or your business. If you can do what we're doing and what we talk about today on VMware or on pure bare metal or on Windows boxes or anything like that, then you can totally do that, and that's totally fine. You could be equally successful as we are using Kubernetes. But what does matter and what really does have an impact, what will actually ultimately impact your business is, can you have short-lived feature branches that you can get into production really, really rapidly? 1 to 2 days is what they say in Accelerate. And so as we think about that, we really felt like for our team, we got a small team of about 7 engineers that run this entire platform for these 2,000 restaurants, and that includes SRE. For a very small team, we felt like the tooling in the Kubernetes world was going to be the key to our success and our ability to do that, so that we could get things into restaurants and make great experiences for you when you go to Chick-fil-A. So at this point, I'm going to hand it off to Caleb, who's going to take us on the next couple steps about some of the engineering problems that we've solved.
Awesome. Thanks, Brian. How's everybody? All right. So we're going to talk about data centers real quick. And quick introduction, so I'm an SRE, Site Reliability Engineer at Chick-fil-A. And we're going to switch gears and talk about data centers real quick. So who here in this room, show of hands, uses AWS? All right. Quite a few of you, not surprised. What about Google Cloud? Any Google Cloud users in production? All right. Perfect. Awesome. And don't be embarrassed. Do you also use, in the South we call it Azure, but I think it's Azure. Awesome. So a couple people in the room that have been forced to use it. Anyway, that was a joke, and that was that fell flat. But anyways, these are our inspirations. So these are some of the data centers they have in the US. All 3 of these guys, despite the Azure joke, are really good at what they do. But that being said, they just didn't quite serve our needs. So I'm extremely happy to announce, and very excited to announce, that today we're going to be launching Cloudflare, where it is our pleasure to serve you. That was also a lame joke. Apparently, you guys are a tough crowd. No, so I say that in jest. This is a map of all of our restaurants that we're putting Kubernetes clusters in. And it is a joke slide, but there's a little bit of truth to it, and that is that as much as we rely on these cloud providers, the problem set that we had, especially as an SRE, I'm very interested in this problem set, is that we have intermittent connectivity. So there's a certain amount of work that had to happen at the compute level at the restaurant. So in order to do that reliably, the question was, how, without paying millions and millions of dollars, are we going to put miniature data centers in each restaurant that are self-healing, highly available, and do it with 7 people? So it's not like we had this big, massive budget and this big, massive team in order to launch this. So we ended up deciding to build our own Kubernetes clusters on these little guys. These are called NUCs, Next Unit of Compute. 8 gigs of RAM, solid-state drive, quad-core processor. Not a very impressive one, but it gets the job done. You can see it's tiny. We used a Chick-fil-A sandwich for scale. So if you haven't been to Chick-fil-A, you should go buy a sandwich just so you can understand the scale of it. What these guys are running is a bare metal version of Kubernetes, which I'm gonna dive into. The picture on the right is a nice picture of some of the reality of the situations we're dealing with. So I mean, we don't have great temperature control. They may or may not be in a cabinet. They could be sitting up near the ceiling somewhere. This is a restaurant, right? So you're dealing with grease and all the other things that come with that. So not only did they need to be reliable and be able to set themselves up, but they also need to be able to survive in conditions like this. So here's the things I'm going to cover. We're going to talk about how we chose to build and repair these clusters, how we do deployments. I'm going to talk about some lessons that I've learned as an SRE specifically in dealing with this. And then I'm going to hand it back over to Brian, and he's going to talk about Fleet, which is another thing we are excited about that we've actually open sourced. Will open source in the near future. And our deployment process is very, very interesting. So I purposefully put the goal at the top, code to prod. So again, as an SRE, and I really want to emphasize this to any engineers in the room, it's so easy to see a problem and fix it. But at the end of the day, if it's not helping me actually get code into production or helping another team actually get code into production, then it's really ultimately a waste of time. It makes me feel good, but it doesn't actually help the business. So I just want to emphasize every problem that we tackled, we looked at it through that filter. Another thing is it needed to be simple enough to be installed by a non-technical installer. So we have a technical team that goes out to each restaurant that will be doing this install, but these are not Kubernetes engineers. They don't know anything about NUX, et cetera. These are skilled technologists, but in different areas. The other thing is if a device dies or a cluster dies, we need to be able to drop ship to the restaurant and have an operator, which is the on-site, essentially, owner of that restaurant, be able to unbox it, read some instructions, swap it out, and all the magic happens unsupervised without our team having to take that manpower on. So it was provisioning and healing were definitely some interesting challenges we had to solve. Managing it remotely, so we're not actually allowed to SSH or VPN into the restaurants themselves. Everything that we build has to pull out to us for security reasons. Fryers and some other sensitive information, or sensitive devices are controlled by these, and as you can imagine, we don't want restaurants going up in flames because we didn't take security seriously. So that's another challenge I'm going to talk through in a little bit more detail later. They had to be able to automatically discover themselves, so it doesn't matter if it's one device or 3 devices or 7 devices, they need to be able to talk to each other, cluster up, heal themselves if some of them drop out of the cluster. And that brings me to the last point, which is self-healing and high availability. So this graph shows 2 experiences. The first top is what an installer or an operator sees when they install the device. So I'm going to walk through that, and then the second row of boxes shows all the magic that's happening in these tiny little NUC devices as all that happens. So the installer receives a device, unboxes it, plugs it in, gives it power, gives it Ethernet, and then he or she goes to a portal called Sherlock, something we created internally for ourselves, and logs in with their username and password, and then the device has already started talking to Sherlock, and they approve, yes, I really did install this device. Yes, I really do approve that this device should be at this restaurant. So essentially, it's our way of trusting that device on our network. The second thing that they see is it goes into a provisioning status. So again, they've logged in, they've hit yes so far. It goes into a provisioning status. There's a bunch of magic I'll talk about in a moment, and then it goes into a clustering status, and then it hits online. And if they hit any issues on the way, they give us a call, and we'll figure out what's going on remotely. So all the magic that's happening underneath that and the tools that we've used in order to accomplish it, first is getting the actual golden image on the NUCs. And we use an MVP model, so don't judge us, but we got the job done. We use Ansible to script out what all should be on those NUCs. So anything, the golden image is built meticulously through infrastructure as code, so we know exactly what's on these devices. We base it on Ubuntu 18.04. 16.04 would have been an easier path for us, but honestly, upgrading to 18.04 down the road probably would have been a harder path than just using the latest version now. Definitely, side note, some interesting networking challenges with 18.04. I think they, it's better than 16.04, but it's definitely challenging. And then we use Clonezilla to essentially, once we know, okay, this is what a NUC should look like, we pull that image off, and we use Clonezilla to blast it out to the other NUCs. This is prior to shipment. Then they get shipped out to the installer unboxes them, everything I just described happens, they power up, register with Sherlock, which is the internal thing that we built. The next thing they do is, there's an internal project we use called Highlander. There can be only one. This is the part of the talk where I pull a sword out, but they took it at LaGuardia, and they haven't given it back to me. Anyways, I'm going to just not give any more jokes. So Highlander, essentially, they all talk to each other, and they elect a leader, and that leader is the one that will then do the clustering process, get all the nodes together, and make everything happen. And if that leader dies, Highlander will re-elect another leader, and it'll continue until it'll fight all the way down to one box if it has to. And then Lord of the Flies style, once a leader emerges, that leader will RKE up. Now this is Rancher's engine that they use to create Kubernetes clusters. And I think it's the next slide. It's one of the next upcoming slides. I'll walk you through why we chose that and the other solutions we looked at, what we liked about them, what we didn't like about them. That whole process of clustering Kubernetes is like under 3 minutes with RKE. It's pretty amazing. Little confession, which it took me like 2.5 weeks the first time I built my first Kubernetes cluster by hand, from scratch. So 3 minutes or so is very appealing to me. The next thing it does is, so at this point we have a Kubernetes cluster. Doesn't have any services installed on it yet. It works at the restaurant, but I'm blind to it. I can't see it. I can't touch it. I can't log into it. I can't do anything to it. So the last thing it does is that we use something we open sourced last night, actually, called Hooves Up. It enrolls itself into AWS SSM. Now, SSM is a technology where you install local agent. It pulls AWS, and it says, hey, do you have any commands I need to run locally on the box? And so we can actually do fleet management as if we're SSH into those boxes without ever having to open a port or do anything like that. We can send a command out to thousands of devices and get responses back in under a minute. This is pretty awesome. And then the last piece, so now I've got a cluster. It's working. I can touch it, but it doesn't have any of our actual services installed on it yet. And Fleet, which Brian will touch on, is our way of rolling those services out. Highlander. So let me check my time. Sorry, I don't want to go over time here. Perfect. So I already talked to this a little bit, so I'm going to kind of blow through this, but we use UDP for the devices to find each other, talk to each other, and elect a leader. This is actually running as a pod on Kubernetes, so it's a small little microservice that we built. Once they talk to each other and somebody picks a leader, that leader goes, okay, I see 3 devices or 5 devices or however on the network, and it begins the RKE up process that actually clusters the devices. We also use OAuth in that process so that we can access our custom Docker repository and some of our other custom components. So it also has OAuth built into it. And it'll install a few basic pods that we need, such as Istio for Ingress, and the control plane itself. One thing I do want to say about Istio, so originally we were using Nginx. We ended up going with Istio for a variety of reasons, but one of the things that I really love about it as an SRE is it gives me really fine-grained control over where I send and what percentage of traffic I send to what devices. So in the case of a Canary deployment, if I had Nginx and I had 3 pods running on 3 devices, I would have to send 33% of my traffic to V2 of whatever we deploy. Istio allows me to throttle that, so I could send 1% of my traffic to a new version, check the logs, and then proceed. It's just way more tunable in that regard. So initializing clusters. So these are some solutions that we went through and ultimately ended up abandoning before we settled on RKE. So we really, 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 really love COPS. We use it in AWS. It's very easy. It's very robust. It's easy to interface with and reason with. However, no bare metal option. And unfortunately, we're doing 6,000 bare metal devices. So, unfortunately, that was out of the running. I think they've either just published or about to publish their bare metal solution, so we might revisit that. Obviously, I would assume that it's probably going to need a little bit of work when it comes out at first. KubeSpray over the last couple of years has kind of been the de facto way of building Kubernetes clusters in a I almost want to use the word reliable fashion. Unfortunately, KubeSpray essentially is this really massive Ansible repo that does a whole bunch of stuff, and it's very impressive. And for the early solutions of Kubernetes on bare metal, props to the team. I really have nothing negative to say. The problem that we had is it just was taking way too long to provision clusters. So it could take 45 minutes for that to finish. And then if it died in the middle because a repo wasn't available or there was a connectivity problem, it was extremely hard to go find state again and restart, especially the way that it was generating certificates, et cetera. So shout out to KubeSpray, it just didn't work for our use case. kubeadmin, again, 7 engineers, 2,000 clusters. kubeadmin's probably the proper way to do it. We just didn't have time to roll our own Kubernetes clustering solution. But in the future, we probably will take another look at kubeadmin. It's a very robust tool. We ended up settling on RKE primarily because of how fast it was and also because of how easy it was. So currently, you set up a configuration file, you have the RKE repo locally, you compile it, you hit go, and as long as it has the correct locations of the other nodes, a few minutes later, you'll have a Kubernetes cluster on Bare Metal. The biggest problem that we have with RKE is that it's so good at what it does, we don't really understand what it does. So hopefully in the future, either we can understand it a little bit better or use a solution that we're a little bit more comfortable with. So we have magical clusters. We don't really know how they work. It also does make it easy to break because it does so much magic under the hood. If you go in and you start messing with a control plane, afterwards, it can be, I don't want to use the word brittle. It's just, you just really have to know what you're doing to not break it, which I've never done. I haven't hosted Kubernetes clusters at all. I've hosted plenty. So anyways, so resetting cluster state. So one big concern we had was, what if we push something out? We don't, there isn't a Hyper-V. There's nothing that we have access to that if we really mess this stuff up, we don't want to hose millions of dollars with hardware. And so we settled on something that would allow us to reset cluster state using overlay FS. I'm sure you guys are familiar with overlay FS, but if you're not, you essentially, every change on the box on the hard drive, every change gets added as a file addition, much like Git, kind of the concept with version control. And if something happens, when the box boots up, the first thing it does is it reaches out to us and it says, hey, I'm online. Should I wipe myself or should I proceed? And our service will say, nope, you're good, proceed, and it'll continue. But if we have a problem, if we royally messed up a cluster or a particular box, we can send it a reboot command, and then we can tell it needs to wipe itself, and it will actually reset itself to the original state that it arrived in any given number of months ago. So it's our way to safely insulate ourselves from bricking 6,000 devices that we don't even have access to. Hooves Up. So this is what we open sourced last night. It's a dead simple script, but it solves a big problem that we had. And as I've described, we need to be able to touch these devices. We can't SSH or tunnel to them. So AWS SSM, Simple Systems Manager, is an agent that's installed on the box, pulls AWS, and waits for any commands that we've fed AWS. The problem is this is all unattended, right? So I'm not on site making sure that these things are set up properly. So we wrote this little script, this Hooves Up script. It's a little Ansible script. You can point it at a bare metal device. It will install SSM. The only thing you have to really supply it is your own AWS credentials. And in there, we lay out what credentials you need to supply it in order to be secure, but also allow the devices to enroll themselves. And then it also installs a cron job, and the cron job will check the device. And if it's not currently enrolled and functional in your AWS account, it will then use your AWS credentials to enroll itself into that account. And the nice thing about those credentials, too, is if somebody swipes them, all they can do is add more devices to your account, which that's not really damaging at all. So, so anyways, we open sourced that. Check it out. Let's see. Oop. There we go. So these are some lessons learned from an SRE. I'm going to jump down to the picture because I love the picture. Always, always, always go with MVP. So this was a very, very difficult, very large-scale problem. And there was a lot of different ways we could have solved it. But the emphasis instead was, what is the absolute minimum we can slap on a box and get into a restaurant to just get it done? So I just want to emphasize, we probably could have dragged this project out for years and still not gotten anywhere. And the funny thing about dragging projects out is by the time you're done, ready to deliver, there's a better solution that's already been developed that you now want to switch to. Not that that happened with Docker Swarm at all. But I just want to emphasize, as an SRE, get into production, make it MVP, swallow your ego, just get the job done, even if it's not pretty. The other thing I want to emphasize is really, really use Kubernetes features. The team has put a lot of thought and a lot of effort around the world, really, into the Kubernetes proper, as well as the repository of all the different tools that they have. And I'm telling you, again, not that this has ever happened to me, because it has, but if you don't pay attention on what Kubernetes is offering, you're going to go solve a problem and then find out a week into working on that problem that there's a repository that's already out there that's already solved that problem for you. So trust that the Kubernetes team has thought through a lot of deployment issues and rollback issues, and it's unbelievable, the tool is. But it's also very complex, and a lot of this information is spread out and not well documented yet. So you're going to have to put the work into going out and getting to know these features, but please use them. Don't try to do Kubernetes at scale, thousands of clusters, if you don't have really good logging. You are just setting landmines for yourself down the road, because when everything blows up, and it will, hunting around amongst many, many boxes and control planes is just a terrible idea. I'm sure a lot of you guys are already sold on unit testing. That's just a de facto standard, but I want to introduce health checking within Kubernetes. This is, as an SRE, this is kind of the new form of unit testing, in my opinion. Write health checks that Kubernetes relies on that are deep, that are generating real calls through your code, that are reliable, that are going to catch as many things in your microservice application as high up the stack as you can, because Kubernetes magic is really based on knowing the current state of your application. And if you don't write good health checks, your app could be down, and it's not telling Kubernetes that it's down. So really take health checks seriously. In Kubernetes, they call it Health Z. I just can't emphasize that enough, because when an outage occurs and it becomes lengthy, 99% of the time, it could have been prevented with a better health check. And also, the way that Kubernetes works, give everything metrics. So give your apps metrics that, again, as an SRE, I can pull your metrics now, and I can do things to help your application stay online. Don't just blow by the health checking and the metrics, because it will make your life a lot easier. You'll sleep more. You will read about the outage in the morning and how it healed itself more if you do these things. And I think that's it.
All right. Thanks, Caleb.
Thank you, everybody.
So to reemphasize, what's really unique to us, I think, is many people have Kubernetes clusters, but a lot of times they maybe have one or two, and they're running tens, hundreds, thousands, hundreds of thousands of containers. Our scale is very unique in that we have lots and lots of clusters that have tens of containers that run on them. So it creates an interesting challenge in the area of thinking about how do you do deployments. So I'll tell you a little bit more about that. Obviously, just told you, we have 6,000 nodes, 2,000 clusters. That's a lot of targets. That comes with its own challenges. Connectivity, being up or down at any given time to those, all kinds of things. Because of the number, that becomes a very interesting challenge to solve. We also have what I would describe as complex success or fail criteria. So to explain what I mean by that, if I have a deployment that I want to target 1,000 clusters with, and 900 of them succeed, but 100 fail, was that a success? Is that a fail and everybody rolls back? Is that a manual one-off, find a solution for those 100? Do they somehow automatically self-heal? Does somebody get involved? It's not an easy problem space when you think about targeting that many different environments and having to be able to do that in the fashion we want, where we want to continually deliver things to production to have an impact as quick as possible. And then to make it further, even more complicated, we have an array of different types of applications. So we have microservices that are REST-oriented, but we also have things that use WebSockets or MQTT, which are persistent connections. What that means is it's not easy to just say, bring up a new one. Sometimes you have to think about connection draining and managing different things like that that add some complexity. So how do we think about this problem? We considered a couple things, and we've said MVP 1,000 times. The simplest thing that we thought about starting with was just saying, we already have some messaging channels that we can use for restaurants, SQS and AWS, MQTT, which we use extensively. We could just send a message down to the restaurant and have it apply it. Really simple, report back some status. That would totally work. Grab my water. Sorry. So we could have done that. We also thought using kube control, Kubernetes native, great tool, really powerful, constantly being iterated on, does a lot of great stuff. Challenge with that is what we explained before. We don't want to have, and we don't have a channel to go directly from our control plane into our restaurants. And naturally, if you have a lot of cases where you're doing that, you do have a point where if somebody compromises that one spot, they may have the ability to compromise your entire infrastructure fairly easily. So there's just some risks around that that make that challenging. And then we actually went down the road a good bit with Helm, and we like Helm. The templating feature of Helm is pretty cool. If you haven't used Helm before, it's kind of a deployment and packaging manager, and the templating piece is basically a way to stub out for different environments what values you want to template in, and you give it some files to say, make the Kubernetes deployment file, the deployment YAML, the ingress YAML, the service YAML, make them look this way. So we liked Helm, but Helm, again, requires direct access to the cluster. And also, while we like the templating, there's some things in there as well around the way it does deploys that make some of the more sophisticated things like a canary deployment or a blue-green deployment pretty challenging. So we decided not to do any of these things, and instead wrong button. We created Fleet. So I want to tell you what the design goals were for Fleet and what we did, and then I'm going to do a quick walkthrough just to explain how it works. It's super simple, but I think pretty cool also. So we want something simple and really easy for developers to use, and we wanted to be able to do self-service on that as well for the other teams that use our platform. Totally wanted to be declarative in approach. So no imperative, making the state of a cluster change on the fly. We really wanted everything infrastructure as code effectively, but not just at the application level, also really being able to go back and look at a given restaurant and be able to see what should this restaurant actually look like right now? What's the to be or the desired state? Compare that to what the actual state is and be able to find differences where we've had drift or where something looked like it was successful and it wasn't, and things like that. So we definitely wanted to be declarative in nature. I mentioned different kinds of deployment models just a second ago. We want to be able to do that and give flexibility to our teams. Thank you, guys. I appreciate it. We wanted to have the ability to roll out over a really flexible time period, right? So in a restaurant where certain functions are business critical for us, they might actually impact taking orders. Those changes may roll out with some teams to all restaurants over a day or a week or a month or maybe multiple months. And so we wanted to be able to support that and not dictate how people actually rolled out their apps and put that choice in the hands of the team. We wanted to say standard Kubernetes as much as possible, and then of course we wanted full visibility into this whole pipeline and everything that it did. So we created Fleet. Fleet has these components. This is pretty simple. There's a client. There can be many clients. There's a REST API and a CLI as well. So you can get webhook it or whatever you want to interact with it from your own team's deployment and build process. There's, of course, an API. And what we do there is basically code gen, very much like what Helm does with templating. We code gen some stuff. We put some unique Chick-fil-A things into the containers. And we build these files that Kube Control uses to make deployments happen. So the ingress.yaml, the service.yaml, and the deployment.yaml files. Fleet Server also manages a Git repository, which we call the Atlas. We'll hit that in just a second. And then it also is the place where API calls come back to track status of deployments. So Atlas is really a Git instance with a repository for every single one of our clusters. That's in any environment. So we can, at any given time, looking at Git, see to-be state of every single cluster we have in all of our environments. And essentially what you have inside of that is you have a folder per application, and then you have these files that were generated inside of there, and then some metadata that we tag on to make it easy to track them through their lifecycle. So how does this all actually get into a restaurant? This is all control plane side stuff. We have a tool called Vessel that we built, and then we found that Kubernetes actually had solved this problem, so we'll probably change to that later. But for now, we're using Vessel, and Vessel is a piece that actually lives in the restaurant Kubernetes cluster, the target, and it basically does a git pull, a kube control apply, check the status of the pod and see what happened, and then report back. Super, super simple, but also very effective. And then, of course, there's dashboards on top of this so people can reason about what's going on. So a quick walkthrough. I told you there's templates. If you've seen Helm, you probably think you're looking at Helm. This is really, really easy. And this is a simple example where we basically can template out some different fields that a team wants to take control of for their specific application. You can't see ports on here, I don't think, but you can have one-to-many ports. You template in secrets and things of that nature. Then we've got the Atlas. It literally is, this is just a demo environment, but we've literally got 3 clusters here, and if we drilled into this, we'd be able to see the state of all of them, see the applications in there, and see those files I talked about. And then what you would do in a simple form is if you wanted to do a deployment for this app called auth server edge 3, and you wanted to make it have 4 replicas and it's going to pull this Docker image that isn't real, so people don't watch this and then mess with our Docker registry. It's going to pull that image down, and here we've targeted 2 clusters, which are 2 of our labs in our request. So what that's going to do is template out some of the files. I just put deployment in here so you can see, but I actually ran through this example offline so we didn't have demo issues. And you can see here it's auth server, edge, it's got 4 replicas, et cetera. So we've kind of created code gen, and we of course have our generated by fleet YAR that's in there. You got to have that. So definitely. And then so what you get is I told you it manages the atlas. So inside of the atlas, you would actually be able to go and see exactly what changed in this particular iteration of somebody requesting a deploy. So they sent that JSON object in. We did some code gen. We wrote it to the Git repository for the restaurant. And then we can actually go see the change from 3 replicas to 4. And we actually have this deployment hash that gets updated so you can see exactly, tracing back. This was over 100 clusters. What happened over that whole 100 cluster deployment? This is your unique identifier for that. What happened in the actual restaurant? The Git hash at the head of the branch, that's actually our indicator for that iteration, the actual at restaurant level deployment. And I'll show you what that looks like here. In this case, we use Dynamo. We'll probably change this eventually, but right now it works for us. And we just have a Dynamo table where we keep these records. So you can see that deploy hash we generated, the Git hash from the restaurant. It targeted these 2 clusters, and then the status of that one's pending. Another one had a status of crash loop back off. But a super easy way to capture some data. There's some more fields off to the right, but capture data and metadata about deployments and be able to have a real clear picture of what happened. And again, I think one of the most important things here is that this is not a super sophisticated solution, and it's almost like, it almost feels weird in a sense, going to a conference and talking about, hey, we use Git. But I think that's really cool that we can take advantage of tools that are already out there that are really powerful, wrap some stuff around them that fits our use case, and be able to deliver things that have an impact really quickly. So there's a lot of great advantages to this. There's some, definitely some downsides, but we think this is a solution we're going to stick with for quite a while, and we're probably going to drop it out as an open source thing, just even though it's simple, just for people to look at and get their minds thinking about how deployments to lots of clusters ultimately work. So with that, I want to mention where you can find us. So Brian and Caleb, we're on LinkedIn and Twitter. We'd love for you to reach out to us and connect if you want to. Chick-fil-A is also on Medium, and there's a blog post that we put up, I think, a day ago that talks a lot more about what we do with bare metal clustering. So love for you to check that out and follow us if you like what you see. And then we're also in GitHub at Chick-fil-A, chick-fil-A, and we'd love for you to check out the projects we have there. And finally, I'll mention there's Gopher logos everywhere because we're big Go advocates when it comes to the applications we build. So lots of Gophers in our open source projects that'll be out there, but like to have fun with those as we go. So with that, we really appreciate you guys taking the time to come and listen to us, and we'd love to answer some questions. So Andrew, I think we're going to turn it over to you for that.
Build it, man.
So there is a microphone. Come up here and ask questions. We probably have about 10 more minutes since we started about 5 minutes late. So.
Yeah, I was curious why you guys settled on the architecture the way you described it. For example, another option that comes to mind is, could you have your clusters in the cloud, and the stores would be talking to those clusters when you could have namespaces where for your restaurants?
Yeah.
Why you didn't go with that option?
Okay, yeah, great question, thank you. So just to reiterate, question is basically why actually put computing in the restaurant at the edge? Why not do something with a Kubernetes cluster in the cloud where you separate things by namespace or something along those lines? So definitely, if we could have done everything that we needed to do from a business perspective and just use the cloud, we totally would have done that because it would be way simpler. There'd be way fewer problems to solve. It really comes back to that idea that we want to be able to build things on top of this platform at the edge that are critical to running our business, which could really mean driving food production and automating some of those cooking processes and things like that. And we have a lot of things where there's a lot of data moving around very rapidly, and we don't feel like we have the network connection quality in 2,000 restaurants. A lot of them are malls with a mall-provided internet connection, right. And then a lot of them can be rural areas where you're not going to get fiber. So we actually wanted to make sure that we could run the business without depending on something outside of the restaurant. So putting the cluster at the edge was the reason for doing that.
Data actually gets persisted on those machines?
Yeah.
And that's a good question. So the question was, does data actually get persisted there? It does, but it's always, it's really transient at the actual restaurant level, and there's a continual egress of that out to our cloud control plane. We have data lake strategy and things like that. So we take all the data that we collect and we send it over there.
But to your question and his point, some of these restaurants, they have network bandwidths that are so challenging, we may actually need to persist it there for an entire day and wait and stream it up at night.
Yeah.
So, so I'm still trying to talk him into just putting it all in the cloud.
Can't do
It
it.
would make my life a lot easier. But there's too many drawbacks. At the end of the day, internet should be able to go down, and as a customer at Chick-fil-A, you shouldn't even know.
Yeah.
You know, your credit card transactions are getting queued up. All the other magic that's happening with the point of sale systems all occurring. The only thing that we can't solve for right is mobile orders, because that needs to come in through a connection. But yeah, the point is that we want zero downtime, not zero as an SRE, as little as possible, right?
Well, thank you for the question.
Great question.
So touching on something you just mentioned, answering his question is, given your point of sale infrastructure, transaction processing, et cetera, how much of that runs directly through this, and what challenges did you face getting that, handling PCI compliance, handling transactional infrastructure, and actually touching the money on these edge systems?
So good question. So today we actually send all of the data from our point of sale from like a button press. So somebody rings in a Chick-fil-A sandwich. As soon as that button is pressed, that generates a message that comes through this infrastructure. We don't run any payment through this. We're actually not in PCI scope at all in our infrastructure in this case. And we do things like end-to-end encryption as well. So encryption at swipe. So the credit card number in a restaurant is never in the clear ever. So we do some things like that. But we will, over time, really in a restaurant like Chick-fil-A, you have registers on the counter where people are ringing in orders, and then the traffic from that ultimately makes its way to screens where people are bagging your food and back in the back where they're preparing things. And that drives actual production. So having outages on what to make actually is really impactful, just as much as internet down, and so we can't process credit in real time. That's really the critical things we have, is being able to ring in orders, be able to take payment, be able to produce the food without people having to yell back everything that's going on. So we do have that second workload that's in the process of moving onto this platform where it's publishing out messages, and that's actually driving the behavior of all the screens, smarter screens basically for our team members to help them know what to prepare.
Over time, we'll have to tackle some of those problems, though.
So as you convert, or as you think about moving payment processing infrastructure to this over time, are there any challenges or interesting
we actually do. So
planning on there?
Yeah, credit actually will not go through here, so we don't have to worry about that. It actually goes straight out to the internet. It's on a separate VLAN and things of that nature. So it's not a problem fortunately, it's not a problem we have to solve in any time in the near future.
Was there consideration for how much or how little a store operator needs to know about this? Is it meant to be completely hands-off for them? And how do they interact with it when things go wrong?
Yeah, great question. Want me to take it again?
Sure.
Okay, so we really put a lot of thought into making sure that, so again, complexity in the restaurant, right? So taking something and giving somebody who's already super busy leading a team of 100 people who are trying to serve hundreds of thousands of customers in a month and saying, hey, here's another thing for you to know and that you need to know about and you need to touch. Not good. We didn't want to do that. That adds more complexity. It doesn't simplify. So while we do communicate the fact that these boxes in the restaurant exist and they can physically see them, the only thing that we ever ask them to do, the owner-operator to do, is if they get a replacement for a failed device, to open it and unbox it, follow the instructions, which are swapping cables, and it'll boot itself back up and return to service. And then if for some reason that doesn't happen and they leave it sitting there because they're busy, our help desk will initiate a ticket with our help desk to have them call and walk the operator through it after about 48 hours so that we can make sure, we have 3 nodes so we can keep running. It's not critical, but it should another one fail or a switch fail that we're dependent on. Our network architecture is resilient as well, and so each node is on a different switch. Such that we don't have any single points of failure overall in the architecture. But if something else weird happens, we could get to a point where we have 1 node left, which can create some weird split brain problems in the restaurant, and also could be not enough capacity to run the things we need to run. Great question. Any others? Okay, well, Caleb and I will, I know there'll be another session coming. We'll go hang out outside versus coming up and talking in the front in case anybody wants to chat, and we'd be happy to talk with you. So thank you guys again. Appreciate your time.